Hi everybody. Welcome to video 2 in this lecture where we're discussing phase transitions. In particular, we're interested in the van der Waals gas, which has this equation that we talked about in the last video. And you'll notice that this equation has, at least sometimes, three solutions when you try to solve for v as a function of p naught. Now I've also plotted P naught here. So pressure's on this axis, volume is on this axis, and then these three curves are three different values, so I should say are three different P naught curves for different values of T. All right, so having caught us back up, I'm ready to go on to what I want to talk about in this video, which is how we begin solving the problem of if we set the pressure to a particular value, which volume does the system actually achieve? We see that up here, in any of the three curves, we'll have only one solution for the volume. So for high enough pressure, there's no issue. It will also turn out that for low enough pressure, there's no issue. This range is not infinite. Doesn't go all the way down to zero necessarily. Good. So we only have to care about this range and only for low temperature cases. All right, so how are we going to do this? As we said in the last video, what we really are trying to do is take F into G, which we know is equal to F plus P times V, or really, G is the V Legendre transform of F. That means that G is equal to the min over V of F plus PV. All right. So we identified that these 3 points for this value P are the 3 possible points in V space. So let me mark that. So V1, V2, and V3 that minimize this in the sense that V1, V2, and V3 all satisfy F prime of Vj, where j is 1, 2, or 3, is equal to minus P. All right. But which of these points are minima? To figure that out, we'll need to take a second derivative of f with respect to v and then plug in these values. What we see is that this point will be a minimum, Vj will be a minimum, if and only if the slope of this P naught curve is negative at Vi. I'll let you work out the details here, but it's something that you can figure out with elementary calculus. So in this case, that says that this point or this point, points 1 or 3, might be the global minimum, and at least our local minima of F plus PV. So this middle point is out. Good. But between these two other points, which is the global minimum? So which one is actually bigger? Well, we can restate that question in a slightly different way. We're trying to figure out if F1 plus P, which is the same across both of them, times V1 is greater than F3 plus PV3. Now we can also move all of this to one side of the inequality if we include some negative signs. Okay, Well, now we might be getting somewhere. And the reason that we might be getting somewhere is that this actually looks like an integral evaluated at two endpoints. But what is it an integral of? Well, let's imagine that we're integrating over v. Okay, so we want to do some sort of integral over v and achieve this. And what should we be fixing? Well, let's fix t and n. Then the thing that gives us this would be, and sorry, I am kind of writing this in a silly way. We want to fix t and n along the curve over which we're taking a line integral. So let me just say this is the curve r, where r has fixed t and n. Okay? So this is going to be the derivative with respect to v of f. Move this over a little bit. While fixing t and n times dv. So r has v endpoints. Let's see, v3 at the one end is the beginning, and v1 at the other end is the end. Okay. Then, to get the second term, we're just going to want to integrate p times dv, where p is a constant, over the same curve r. Excellent. Okay, how do we visualize this in this graph? Well, the answer is actually not too hard to see. This, by definition, was our P naught. Was our minus P naught. There we go. So we have that this is greater than 0. So this means we have F1 plus PV1 is greater than F3 plus PV3 if and only if P minus P naught has an integral over R times dV, which is greater than 0. All right. Now, it turns out that we can see this on this graph. It might be best, in fact, to say the exact opposite. So this would give us the condition for when F3 is the solution. So the condition for when V1 is the solution is that the integral over R of P naught, this should have been P superscript naught, minus P times dV is greater than 0. All right. So how do we see that? Well, here's our P naught in blue. And here is the constant curve P, just P. This integral is precisely the area between these two curves. So in this case, it's the negative area in here and the positive area in here. All right, so what does this mean? V1 is the solution exactly when all of this stuff is greater than 0. So we switch from one to the other exactly when this area over here is greater than this area over here. All right, so we have a condition for when V1 is the global minimum and for when V3 is the global minimum, which means that we have something that happens that switches the system in a sort of discontinuous way from achieving volume V1 to achieving volume V3. So now we see a consequence of all of what we just worked out. As we change this value P, at some point, we'll jump from the solution V1 that's over here on the left side to the solution V3 that's over here on the right side. And we'll do that discontinuously in P. That means that V as a function of P for this system is not a continuous function, at least at low temperatures. It also means that G has a first derivative that is also discontinuous. Because G is a function of P, it turns out that you will be able to see that G has a discontinuous first derivative. Maybe it's already obvious actually because V will be discontinuous. But in any case, this is called then a first order phase transition. Now we have something else happen that's very special at this critical T. And that's that these three solutions, V1, V2, and V3, would all collapse into exactly one solution for this value of the pressure here. And that's because our P naught curve here has an inflection point, which is and that's because our function P naught here has an inflection point which is neither a minimum nor a maximum. In fact, the second derivative is 0. The upshot here that I can say without going through all of the math is that for this point, the first derivative will not jump, precisely because changing V a little bit will just change V continuously. But notice that the V function here, so V as a function of P, will have an infinite derivative. The consequence of this turns out to be that G now has a discontinuous second derivative. So let me say here, G prime of P is discontinuous for the first order case. And here, G double prime of P is discontinuous. Now, phase transitions of this type are sometimes called second order phase transitions, exactly because the second derivative is the thing that's vanishing. And then you could cook up exotic examples in which G triple prime is vanishing that are third order, etc. But it turns out that first order phase transitions are so different from all of the rest of the phase transitions that we typically group the others into what are called continuous phase transitions. So this is a continuous phase transition. Again, just to reiterate, the condition that we'll end up using all of the time is that a first order phase transition has a discontinuity in one of the free energy functions somewhere in the state space. Whereas a continuous phase transition has that the free energies themselves have continuous derivatives, but their derivatives may be discontinuous. Now we have one more very important point to mention as we finalize what we're saying in this video, and that is that, in fact, the van der Waals gas has a liquid phase and a gaseous phase. The gas phase is what we get at high temperature. It's what we see here for the pink and green curves. So these two up here. And we could ask ourselves, for the blue curve, which is the gas and which is the liquid? The answer turns out to be something you can work out if you reason through it. Now, down here, when V1 is the solution, we change P a small amount and V changes a small amount. Whereas when V3 is the solution, we change P a small amount and V changes by a large amount. What that means is that the solution over here has a larger compressibility because we change P by a small amount and V changes by a large amount than the solution over here, which means that over here we're looking at a liquid, and over here we're looking at a gas. Good. So maybe that comports with what you would have guessed. A gas is what we would get here at the relatively lower pressures, and a liquid is what we would get here at the relatively higher pressures. Now, one thing that you'll notice if you ever go and try and boil a pot of water is that while most of the water is still liquid, some of it will have turned into steam. The model that we've suggested here, the rectification strategy, gives us that the system is either a liquid or a gas at every point in state space. But we know that that isn't physically true. In the next video, we'll introduce a rectification strategy that lets us be even more sort of fine-grained about what's going on in our simple systems. Thank you so much for watching, and I'll see you in that video.